Hello, my name is Jainam Patel, and today webinar is about laser beam shaping with Aimdraw tailor builds, and we are talking about the laser beam shaping in this webinar. My name is Jainam Patel, and I am a CFD application engineer at Paanduv Application with the 2 years of the experience in the field of the designing and computational modeling. And I have completed my MTech from the VIT Vellore. I have expertise in the mechanical chemical engineering systems and the energy environment systems. Let's begin with the introduction about the LPBF and process challenges. So, laser powder bed fusion or LPBF is a widely used to metal additive manufacturing process. It builds part layer by layer by spreading a thin layer of a metal powder and a selective melting it using a high powered laser. As each layer solidifies, a new layer of a powder is applied, and process repeats to form from the complex 3D parts directly from a digital design. Despite its advantages, LPBF faces the process challenges. Common defects like porosity, keyholing, and lack of fusion are often caused by manifold instability and uneven energy input. These issues can be affected part quality and mechanical performance, making process control critical. Although LPBF enables the fabrication of complex and high performance metal parts, it is prone to several types of defects that can be compromise part quality. Some of the most common includes keyholing, lack of fusion, porosity, spattering and balling, partial melted powder, waviness in the build. These defects are often linked to how energy is delivered during the process. This brings us to the next key topic about the importance of the laser beam shaping in additive manufacturing, which plays a crucial role in controlling manifold behavior and improving overall build quality. So, importance of laser beam shaping in additive manufacturing. In LPBF, the shape of intensity distribution of the laser beam plays a very critical role in the part quality. So why beam shaping? When a standard Gaussian beam is used, there is a very high thermal gradient at the core of the laser spot, often reaching the between temperature which temperature will reach about 10 raised to 6 to the 10 raised to 7 Kelvin per meter. As we move away from the center, hello. Um, as we move away from the center, temperature drops sharply. This uneven heatings leads to high residual stresses and common defects like the cracking and the warping. Additionally, unstable manifolds caused by the uneven energy inputs can be inconsistent layer quality. Overheating in the localized area heating can also cause like this spattering, porosity, and distortion. This is why beam shaping comes in. By tailoring the beam profile, such as using the top hat donut shape and the elliptical shape, we can distribute the laser energy even more evenly. This creates a more uniform heat inputs, stabilize manifold behavior, and improve the overall layer fusion. The results: fewer the defects, better part integrity, and more reliable builds. Shaping the full experimental insights into the laser beam profile. So this slide shows the experimental insight into how different laser beam profile affect the manifold and resulting part quality. On the left, we compare the three common beam shapes: flat top, ring shape, and Gaussian. The flat top profile delivers uniform energy across the spot, leading to stable manifolds and consistent layer fusions. The ring-shaped beam creates an hollow integrity pattern that can reduce the peak heating and help to control the vaporizations, minimizing the defects like the key holding. In contrast, the Gaussian beam, which has a sharp peak in the center, tends to concentrate in a small area. This causes the steep thermal gradients leading to instability and higher chances defects. Now, now on the right side, we see a direct comparison between the standard Gaussian profile and inverse Gaussian or a shape profile. So with the Gaussian beam, the part shows a poor surface quality. Here we can see on this image. Okay, and it has a very finer grain, poor surface quality. Hello. Sorry for the interruptions. Uh, Let me begin with the right side part of the image. With the Gaussian beam, the part shows this poor surface quality on the right side, okay, which has a very fine grain, low relative density. And after using the inverse Gaussian laser beam shape, we got the excellent surface quality, larger grain size with the 50 to 100 micrometer, and the high relative density. So, why simulation for the laser beam shaping? So, while laser beam shaping has a clear benefits, there is a challenging part is the most commercial laser system only offers the basic shapes like the Gaussian shapes or defect shapes. Advancing the profile like the ring shape or the multi-spot beams are either difficult to access the required custom optics. Experimentally, testing the new beam shapes is also the time-consuming, costly, and can carry the risk of damaging the equipments or producing the poor quality parts. This is where simulation becomes the essential. It allows us to explore the wide range of the beam profiles, predict how they influence and manifold behaviors, and optimize the process parameters, all without needing the physical trials. With simulation, we can test ideas quickly, reduce the cost, and gain the insights that would be hard to achieve experimentally. So, looking ahead, the trends is moving towards the smart, programmable laser system. Simulation will be play a very critical role in the designing and validating these adaptive beam control strategies before they are implemented in the real machines. So, before moving with the different shapes of the laser beam shaping, let me start with the that inputs required in the laser beam shape basics. So, standard deviation, quantifying the beam shaping. In laser beam shaping, standard deviation is a key statistical measure used to describe the spread of the beam intensity profile across the space. So, a low standard deviation indicates that the value tends to be close to the mean of the set, and the high standard deviation indicates the value are spread out over the wider range. So that means standard deviation is useful to measure that how much laser beam profile is like spreading across like it will useful to capture how much laser beam spread will happen. So generally, we are using the 4 sigma, which is a 95% of the laser beam spreading. So d4 sigma or the second momentum of width. The d4 sigma defines the beam diameter as 4 times of the standard deviation. D is equal to d4 sigma we are using in the AM PravaH softwares. So this is a widely accepted standard by the ISO for the characterizing the beam width. So why for sigma? So in a Gaussian beam, approximately 95.4% of the total beam power is contained within the plus or minus 2 sigma means total 4 sigma width. So this means the 4 sigma beam diameter effectively captures the 95% of the beam's energy, providing the reliable measure of the usable beam area. So let's understand the laser beam profile. So in AM PravaH software, we can generate the n number of the laser beam shape profile. Among that, I have created this 6 type of the laser beam shapes. User can create the any profile which he wants. Okay, so first one is a Gaussian beam, multi-Gaussian beam, bezel beam, top head beam, ring beam, elliptical Gaussian beams. So these are the laser beam profiles generally commonly used. So first one is a Gaussian beam. So in the Gaussian beam, we can see that it's a very high intensity peak energy on the center, and when we away going away from its radius from the center part, so its intensity will be declined. So user can use this formula to create this 3D shape for the Gaussian beam and provide that radius points and the intensity points in the AM PravaH. Similarly, bezel beam shape. In the bezel beam shape, center part is a Gaussian part, okay, and then the outer side part, which is a ring shape. So here I have created this bezel beam using this formula, and the which bezel beam in this bezel beam Gaussian profile and the ring shape profile I given the same intensity. User can change this intensity by creating the different shape of the profile. Third one is top head beam. So in the top head beam, uh, in the specific radius, it has equal amount of the energy density intensity part. Okay, so its shape is actually look like the top head. Okay, and fourth one is a ring beam. So in the ring beam, which is clearly we can show it's look like the ring shape, and from specific radius part from the center, there is a Gaussian profile is there. When we revolve this part, it will create the ring shape. Multi-Gaussian beam. So in the multi-Gaussian beam, center part is we can see that it's clearly Gaussian beam, and away user can create the n number of the ring shape beam around that. I have created the uh, three shapes of the ring. So in the center peak part, this I have given the intensity of the 100% one. Then next ring shape, I give the 75%, 50%, and then 25%. User can create the n number of the rings by using the AM PravaH software. Sixth one is the elliptical Gaussian beam. So in the elliptical Gaussian beam, which is a Gaussian beam, but in the x and y directions, there is a different radius is there. By using this formula, user can create the elliptical Gaussian beam. So let's begin with the experimental analysis that I have done using the experimental comparison I have done with the AM PravaH software. So on the left side part, there is an experimental image of the ring shape beam, which has a 10% intensity in the center ring and the 90% intensity on the outer side ring. So I take the D4 sigma same as a that reference paper, 205 micrometer material SS316L. Width is D4 sigma is 205 micrometer. Okay, and after that I have run this on the plane surface as taken as a reference as the reference paper, and I got the width and depth which is 190 micrometer and 53.84 micrometer as a depth. So let's compare with the experimental. So from the experimental comparison, width is minus 6.64% lesser than the uh, um, experimental width. Okay, that's why I put that minus, and 5.5% is higher than the experimental depth, and we can see that clearly shape is actually matching with the uh, experimental setup. And let's move forward to the next slide. So I have done the case study of the laser beam shapes on manifold dynamics, where I take the material as a die 6 L4V. Scan speed I take this 1.25. Now you can see that I have taken this 600 micrometer track length and the power is to 80 watt. So this process parameter I have taken, and I have taken these six different laser beam shapes: Gaussian, top hat, elliptical, bezel beam, multi-Gaussian beam, and the ring beam. Now, I have taken the same parameters for this all these six different beams, and only laser beam shapes are changing. Let's see what are the results from that. Here we can see that cross section of the manifold, where elliptical Gaussian, bezel beam, Gaussian beam. top head beam, multi-Gaussian beam, and the ring beams is there, where we can see that on the left side part here, on the elliptical Gaussian beam, which has a peak energy at center, tapering of the towards the edges, and then we can see that its melt pool characteristics that it has the deep narrow melt pool. Similarly, from the flat top head beam, energy concentrated around its perimeter for the top head beam. So we can clearly see that elliptical Gaussian beam, multi-Gaussian beam, and the basal beam shape are removing that. See these tiny gaps. Okay, so they have very clearly high depth. Okay, so that's why they are removing the gaps between the particles and removing the porosity part also there. But there are some disadvantage also of the Gaussian beam and the other beams are that they have the like a very quick uh, heat transfer and the very quick cooling, and their main intensity of the peaks on the center of the Gaussian peak. So that's why there is a defects like keyhole will be generated there, and spatting will be generated there. So further we can see that on top head beam and the ring beam, they have the multiple high intensity peaks. Wait. On the ring beam, we can see that they have energy concentrated around its perimeter, and they have the hollow or wider melt pools and the control depth, which will improve the melt pool stability and they lower the risk of the keyholing and the better surface quality. So for the same top head, we can see that it has a uniform energy across the spot diameter here, top head part, which has a wide, shallow melt pool area, which is a more uniform microstructure we can generate it, and it will be helpful to reduce the thermal gradients, fewer cracks in the pores. So let's move forward to the next slides. On these slides, we can see there is a top view of the uh, melt pool. So elliptical Gaussian beam, and multi-Gaussian beams, and the laser beams. So I have found out that top head beam and the ring beam has a very smooth surface finish and the low temperature on this surface because they have the equally heat distribution on the surface area. And similarly for the other ring shape has the higher the temperature gradient on the surface area, which I will show the temperature plot over line on the next slide. So here is the density profile across the mantle cross section for the different laser rings. We can see that clearly here that okay, we can clearly see that Gaussian beam, elliptical Gaussian, and the multi-Gaussian and basal beams they are very high depth. So they are removing this porosity part that gaps between the particles, and they will remove the porosity type shapes. Okay? And sometimes if they have a high intensity or a high power, they will generate the keyhole effect. So user can use the Aimdraw software to minimizing these defects by doing the multiple simulation and find the optimized process parameter to create the uh, uniform and the good builds. On this slide, we can see that okay. So on this slide, I will show the uh, dynamic thermal profiling using the probe analysis. So we can see that here, this is the powder bed. There's a powder is there, and I have created one line on that powder. So when the laser will move from the uh, line, that line path, we can see that that thermal profiling of that at that specific line at that specific space. So let me show this video. So this one is a temperature profile plot over line where I have taken this same six top head beam, ring beam, laser beam, elliptical Gaussian beam, and multi Gaussian beam. We can clearly see that. Let me pause this video. Yeah. we can clearly see that elliptical Gaussian beam, which has a higher the temperature on the center part, where the actually the I have drawn the line. So after this high intensity peaks of this, all of this laser will show that they have the at that time there is a laser is that there. Okay, so there is a maximum temperature we can see that elliptical Gaussian beam has at a specific length. So this one is starting from the 0 to 850. So this is our length I have taken for the like scaling, like for the measurement of the temperature profile. So we can clearly see that ring beam and the laser beam, which has the lower the temperature on the center part. So they are actually clearly show that their temperature profile is spread over the manifold part. Okay. And elliptical Gaussian and the multi Gaussian has a higher the temperature. So these are the results of the laser beam shape for the width and depth. So I have taken the measurements of the laser beam, elliptical Gaussian, Gaussian, multi Gaussian, and all ring and top end beam. So these are the width and depth in the micrometer I have measured, and I have said that top end beam has the lower the width as well as the depth, and the maximum uh, width is on the Gaussian beam, and the maximum depth is on the multi Gaussian beam. So porosity measurement. So I have also done the porosity measurement in the AM PravaH, and I have found out that basal beam and elliptical Gaussian beam has the lowest porosity, and maximum porosity is on the Gaussian beam profile. So by using this laser beam shape profile and providing the different power and scan speed and different inputs, user can minimize this porosity and make the good build part. Now in this video, I will show I have created the one more analysis, which is the transition between the top head beam profile to ring beam profile, where track length I have taken is the 1000 micrometer, and from starting 500 micrometer, it's a top head beam shape, and after 500 micrometer, it's a ring beam shape. So we can clearly see that there's a transition, and I have used the Python shell script to transition between this profile. User can also create this type of the profile, and he or she can check this depth, width, and the thermal distribution, and compare with the two different shape profile. So on the top head beam, we can see that uh, on the top head beam, we can see that it's a U shape profile, and it has a very higher depth, which is around the 60 70 micrometer, and we can its temperature heat distribution is only on the lower part on the z axis, and its wider part is not so much there. Now we can see the ring shape. So on the ring shape we can see that that melt put is actually look like the square shape. Yeah. So its temperature distribution is around its periphery. So the mostly heat distribution goes around its part on the y directions, not on the z directions. So by making this multiple tracks, user can create this by using the ring shape profile. It can eliminate the uh, keyhole effect as well as the porosity and different effects it can eliminates, also the spattering also. So let me show the next slide. So here is the Aimdraw custom laser GUI. So on the right side, this one is the macro scale LPBF home screen. Okay, and there is an option there on the left side tab, which is a create custom laser. So by clicking that, there is a new tab will open, and on that profile on that we can load the different beam shape profile. Also we can create the multiple different shapes and like custom laser shape profile. So there is an option there, add theta, add radius, and plot beam shape, and user can create, modify, and visualize the different laser beam shapes. So how to create a laser beam shapes in AM PravaH? So in AM PravaH, user requires only the two things. One is radius and one is height point. So in the radius, for the specific theta, so I take the theta is here is 0. So next theta will be 2 pi to complete the revolute of the circle. So on the specific theta 0, I have to provide the radius points. So user can provide the n number of the radius points, as well as user has to provide the y direction uh, intensity points or height points. Our software can automatically take that height points and transfer to the it will be automatically use these points, height points and the intensity points, and it will convert to the optimized beam shape profile which whatever the user require. And there's a three things required. One is intensity or height, second is radius points, and third is the angle. And according to radius points, user has to provide the intensity points or height points. So on this image, this one is a laser shape file. I have created the ring shape by using this laser shape file. So we can see that there's a theta is there. So I taken the theta as a 1.011. Uh, User can take the theta as a 0, but he or she can do like he or she has to complete the revolute of that theta. So I have taken the 1.01 and the second one is 7.29. That difference is 6.28. So, and other things, radius and heights we need to provide. On the left side, there is a first point 0 at the center point, and the final point is 150 micrometer, which is the radius maximum point. According to that, I have provided the height value. So, these are the points we can see for the specific theta. Now, similarly, we have to create for the different theta. User can take the n number of the theta to create the complex shape or irregular shapes. And by providing these points, you have to load the profile in the Aimdraw. So we can create the different shapes in the Aimdraw. These are the very specialty. So conclusion. So conclusion, we have find out that it will improve the surface finish, more uniform heat distribution, reduce residual stress and warping, enhance the manifold stability, lower porosity and spattering, better layer fusion and the build quality, control solidification and microstructure, and improve the mechanical properties. And key insights we have found out from all of this simulation. Gaussian beams, while standard we are actually using, it has increased the defect risk due to the intense center heating and unstable manifold dynamics. In Tofet beams, offers the uniform melting, laser bonding, and the surface finishes, which is actually very good. And the favored of the general defect reduction. On the ring beam side, excels in the thermal management and are ideal for the high value applications, require the maximum precision and stability. So any custom laser beam shapes can be created using the AM PravaH software. So user can create the any complex shape. These are the shape I have created for this webinar, and user can create the different shapes like square shape um, and bell shape and any shape. And if you require any help or need, you can contact the support at the pandav.com. So these are the very good features for the laser beam shaping. Question and answers. If you have any questions or doubts for this laser beam shaping webinar, you can ask me. Okay. So how does the porosity vary with the multiple tracks? So different tracks has a different laser shape profile, and there is a different shapes. There is a different intensities are there. Like let's explain with the ring shape. Okay, on the ring shape we can say that there is a peripheral part. Let me show you. Yeah, on the ring shape, we can say that there is a intensity points on the ring outside part, which is very high intensity. So the heat distribution only happen on the intensity part. There is a no central part as a very high intensity, high intensity. There is a totally zero intensity at the center. So this thermal distribution will cause the uh, profile, different shape, different molecule shape profile. How can we combine the two laser profile like elliptical and top hat and get the both multiple coverage and penetration at the same time? So I think you are talking about this simulation I have done. So at that time I have taken the two different shape of the profile uh, for the laser beam shape profile, and for the first part I have done this one simulation, and I would make this cell script, which is like linked with the Aimdraw, and by using that, it will change the laser beam shape profile. Let me show that this one here. I think we are talking about from transition between the top head or ring shape profile. Is it limited to AM only, or it can be used for any other laser material processing also? Yeah, it can be used to for any laser assisted in the AM process. Yeah. So user can create the n number of the different shapes profile in the LPBF process here. Yes, we can simulate the any laser shapes with this software. But user just need to the radius points, enter intensity points for that, and yeah, we can also create the pulsar shape. Like not as a, we have to provide the laser on off time. So specific time laser is on, then we have to provide the as a scan speed track. There is a laser is off, then again laser is on, and user can create the pulsar laser also by using this technique. Next webinar we will talk about this laser beam shape microstructure evolution also. So that will also helpful to understand the um, microstructure profiles and other stuff. Yeah. Yes. Is there any question or doubts or anything you can ask in the live chat, or you can ask the question to the support at the pandav.com. We will happily to answer you in that also. I think. Thank you everyone for joining in this webinar on the laser beam shape.